Okay, so up to the last class, do you have any doubt, anyone? If you have any question, any doubt that you want to clarify, you can do so. We'll be waiting a minute for others to join. Okay. Uh, After that, we'll start. I think in the previous class, your other friends have joined, right? Right now, I can only see Catherine, Shubham, Vishal, Hitesh sir, Vishwajit, Jigyas, Mario, and Zorian. So, if you people have any question, anything else that you want to clarify, you can do so. Otherwise, if you I think others they should have joined by now. And shall we move ahead? Shall we start the discussion? You let me know if we need to start the discussion. We'll start. Otherwise, we'll be waiting maybe during your whatever is the clarification that you want. Okay, during that time, let me know whether we shall move ahead with this today's class. I am audible, right?
Yes, sir.
Okay. Sir, any clarification? Anything that you want to clarify? Any question that you have?
No, sir.
Okay, you have understood the things, right, after the last class?
Yes, sir.
Okay, so since already we have waited a good amount of time for others to join, so I think we can move ahead with today's discussion. So up to the last class, basically the bell rate working, the different parameters associated with it, and what is the different way of belting, the law of belting. Okay, all those things we have discussed. Later on, different relationship with respect to your bell rate, that is like finding out all those length of bell, then the ratio of the driving the tensions. Okay, so all those things we have already discussed. About centrifugal tension we have discussed, when we have to consider it and what is its effect and all. Okay, similarly all those like sleep, creep, then grounding of pulley, etc., all those concepts already we have discussed. And today we are going to basically go for starting solving certain problem. Okay, in the last class also one small problem we have already solved. So today some build design related problem we can solve. And after the last class, if you can recall, we have also discussed about this particular relationship, very important one with respect to your designing of bell, where we have seen that the maximum tension to which a bell can be subjected, which is given by T. Okay, T is the maximum tension. It can be given by multiplication of the tensile stress in the bell thickness, and the width of the bell. So the you have to take care of the unit. So sigma T, that is the tensile stress in the bell in Newton per meter square, and thickness in meter, thickness of the belt as well as width of the belt in meter. And we already know this is tension is nothing but a kind of force, right? So it's the maximum tension that we are talking about. So from here, if you know about that, what is the belt material and all, and you'll be able to know about the tensile stress in the belt depending on what is the condition of it. Okay, maximum allowable, etc. So similarly, from here, from this relationship, by using this relationship in conjunction with other known relationship that you have for build and all. So you'll be able to find out the design parameters for the build, like the build thickness, build width, etc. Okay, so that basically takes care of the designing of it. So similarly, if you see, if we consider the centrifugal tension also, okay, and this centrifugal tension you must consider when we are talking about high velocity range or the high speed range, then you cannot neglect the centrifugal tension. Okay, so whenever it is high, definitely you have to consider the centrifugal tension. And if you consider centrifugal tension, then we know that if we consider the centrifugal tension, then the maximum tension is nothing but the addition of the tension in the tight side, that is T1, that we have considered a plus, or the addition of your centrifugal tension. So this gives you the total T value. Okay, and that can be written as sigma T into B into T. And this is very useful while considering the build designing problem. Okay, so now we'll start with some other basic problem. Okay, another basic problem that we'll consider. Yesterday also we have solved one problem where we have considered the sleep and all. Okay, and today also another this kind of problem will start. We'll start with the easy problem, and then the region related problem will start. Okay, so let me read out the question. Okay, question statement. So what does it say? It says that a shaft it runs at 80 rpm and drives under shaft at 150 rpm through bell rate. So from this first statement itself, which is very evident, it's a bell rate problem. And this is the nothing but which one is the driver, which one is the driven. I believe from the which drives one. Okay, depending on that, you'll be able to find out which one is the driver and driven. Next, this said that the diameter of the driving pulley is 600 millimeter, and from this whatever is the dimension dimension of the one of the pulley is given, that is the driving pulley, and both the velocities are given. Okay, so from there you have to determine the diameter of the driven pulley. Okay, and the two conditions are given for two conditions. When first one is when a belt of thickness 5 millimeter you are using and total slip is 4%. And next consider is you have to consider when the same belt, that is the belt of thickness 5 millimeter only you are using, but slip is 2% on each pulley. It is not the total slip, but 2% on each. Okay, and here it is total slip. Okay, so I already know this slip is given in percentage slip. So it's a very simple problem. So N2, N1, those things are already given, and you can directly use the formula for velocity ratio and considering the belt thickness as well as the slip that you have to consider. So while solving, what we know, so we have started with the, you can always write down the given data. Okay, so always it's good to write down the given data, so it's important. Then so given data I'll write down. Okay, given data regarding the whatever is the bell thickness, that is T, similarly N1 and N2. Okay, so if I first write down the given data, after that we are actually we have the velocity ratio expression for bell rate as this. Okay, we can write N2 by N1 equal to D1 plus T divided by D2 plus T. Okay, so this is basically considering the thickness actually. Okay, so and as we know from this particular condition itself, so we are saying that there is a total slip of 4%. So effect of slip in velocity ratio, you already know it's nothing but it actually reduces the velocity ratio. So now we are considering this particular slip. Okay, so either you can write like this, okay, this effect of slip, or you can also write like 1 minus s by 100. That way also you can write. This is not just the next step that we are writing. Okay, so this is the, we know that effect of slip in velocity ratio is it reduces the velocity ratio. Okay, and as we are considering the thickness, so it is n2 by n1 becomes d1 plus t divided by d2 plus t whole into 1 minus s by 100. So now after that, it's just like it's a very simple problem only. Only the given data you should be able to properly analyze and use it. And so N2 is already given as 150 rpm. It drives the another shaft at 150 rpm. So N2 is 150 rpm. So 80 rpm is the N1. Okay, and the diameter of the driving pulley is given. Okay, D1 is given. That means okay, and D2 you need to find out. So D1 is given. You can either use small d or capital D depending on your advantage. Just uh, let like clarify it. Suppose diameter of suppose driving pulley or which one is this. Okay, so you can use this. Okay, d1 is given and d2 we need to find out considering whatever is the slip consideration that we have given. Now here the total slip is given as 4%, so there is no problem. Directly 4 we can use. Okay, and ultimately it will just solve it. Okay, d2 d1 is already given, d1 we have used it. Similarly the thickness of the bell material is already given, so d2 is unknown, it needs to be found out. Okay, and only one unknown and the others are known, so d2 very easily it can be found out. So the diameter of the pulley that need to be used is 304.8 millimeter. So this is by considering a total slip of 4%. Now next consideration is you have to consider slip of 2% on each pulley, both the pulleys. Okay, so now, if you recall from the while we have solved the particular expression for finding out the effect of your sleep in the velocity ratio, then we have seen that the total sleep is given by sleep in first pulley plus sleep in, that is S1 and S2 if we consider as the sleep in the driving and the driven pulley, okay, percentage sleep. So then the total sleep as it can be given as S1 plus S2 minus 0.01 into S1 S2. That is from the derivation already we have seen. So this is the total slip. So now here previously total slip as was given directly 4%. So now it is given a 2% slip on each pulley. So that is S1 also is 2%, S2 also is 2%. So directly we are using this value of S1, S2 to like that, and the total resultant slip is 3.94. Okay, that means it's not just the addition of 2 plus 2 equal to 4%, but it changes like this. Okay, and now once the S is now known, so rest is similar. Rest is just like the previous case. The velocity ratio n2 by n1 equal to, we can get it from d1 plus t divided by d2 into t whole into either 1 minus s by 100, or otherwise 1 minus s by 100 will become 100 minus s divided by 100. Okay, if you take the LCM. So that is the case. Okay. So after that, we have obtained some other values of very 304.9 millimeter. It's just a little bit changes there, but the thing is, from here we have actually shown that this percentage slip, okay, on both the pulleys, if you consider separately, okay, it is not exactly as same of the addition of both the pulleys. That is the total pulley, total stick is not like that, but somewhat it is reduced. And what is the reduction factor? Reduction factor is 0.01 times the S1 into S2. Okay, so with this actually this problem is solved. Very easy one, very small one. Let me know whether you have understood or not.
Understood, sir.
Okay, others, what about others? I hope all of you have
Yes,
understood.
sir.
Okay, thank you. So now I believe we are ready with the, already we have solved two small problems, easy problems. Now uh, uh, we are in a position to solve somewhat better problem. Okay, better means somewhat more complex problem. These are easy only. Just the all those relationships you should know. You should be able to use them properly as well as using the proper unit system. Okay. So now what this particular problem statement states, it says that the following data it relates to a flat bill rate. So from here, what is the data that we have obtained? It's a flat bill rate, not a free bill or something else. It's flat bill rate. So whatever is the relationship that holds good for flat bill, so those things will hold good. Now, what are the different data that is given? So power transmitted is 18 kilowatt. So P, power transmitted P is 18 kilowatt. So we'll convert it to watt. So it becomes 18 into 10 to the power 3 watt. Okay. Then the pulley diameter is given as 180 centimeter. So pulley diameter D as 180 centimeter. Well, we are converting to meter. Okay. Angle of contact is given as 175 degrees. So theta is 175 degree. So here itself you can convert it to radian, no problem. Okay, by doing pi by a 1t. Okay, or because later on, if you recall the ratio of the tension, that particular formula, which will be useful here also. So there, that e to the power mu theta was there, which should be considered, that theta should be considered in radian. So that's up to you. Here itself you can change it to convert it to radian and take the below, or otherwise in the while solving also you can do that, no problem. Next, speed of the pulley is given as 300 rpm. So n is given as 300 rpm. Coefficient of friction between belt and the pulley surface is given as 0.3. That is mu equal to 0.3. Okay, and here the permissible stress for the belt is given as 300 Newton per centimeter square. So sigma is 300 Newton per centimeter square. Okay, this itself is nothing but that tensile stress only. Okay, maximum tensile stress actually. Sigma T also you can consider, no problem. So now we are converting this particular Newton per centimeter square, this unit to Newton per meter square, and that gives you 300 whole into 10 to the power 4 Newton per meter square. Okay, so that is after conversion. Similarly, it is given belt thickness is 8 millimeter. So T, small t, 8 millimeter, we have converted to meter. Okay, so it will be multiplied by 10 to the minus 3 for converting to meter. And belt material density is given as this. Okay, so rho is given, belt material density 0.95 into 10 to the minus 3 gram per centimeter cube. Okay, so this unit will be converting to kg per meter cube. Okay, and from here, from this given data, what is being asked, you have to determine the width of the belt, which will be required for meeting this particular condition, and taking centrifugal tension into account. That means, so we have to consider the centrifugal tension TC. Okay, so that we have to consider, and width of the belt B, it is required to be found out. Okay, up to this much, I hope it's clear. What are the given data, how we have obtained the data, how we have correlated. Let me know. I hope yes. Okay. So
Yes,
now,
sir.
okay, thank you. Now we'll start with this main problem. Okay, solving the main problem. So what are the things that we have? Okay, it said that the maximum your permissible stress dosings are given. Okay, and the design parameter, that one of the design parameter, like the width of the belt, it will be required to find out, and we have already the thickness, etc. those things are given. So now we can write the maximum tension to which the belt can be subjected, that is the T, as the multiplication of sigma into A. Okay, tension is nothing but a kind of force. It is something like, as if this is the stress you already know. Okay, it's something like this expression is something like this. I believe all of you already know. F upon A, that gives you the stress. Okay, it is somewhat like this. Okay, so here in our case, it is nothing but this particular cross section area of this particular belt. Okay, and this is nothing but the, we're talking about the tension force. Okay, so that means T equal to sigma A. Okay, so that is what we can write. And now sigma is given, no problem. And A, this area, cross sectional area of the belt, how we can get? We can multiply the width of the belt with its thickness. Okay, and this is a flat belt, so cross sectional area is, what is the cross section area of flat belt? It's a rectangular cross section, flat belt. Okay, so for that, that area, this cross section area, it can be obtained by multiplication of this B width into this thickness, right? So we can write sigma equal to T equal to sigma BT. Okay. So just now also in the previous like topic also we have considered this. Okay. Sigma BT gives you the maximum transfer. Okay. So after this, we have just put the whatever is the value given for sigma. It is already, we have this sigma equal 300 into 10 to the power 4 Newton per meter square. B is unknown, that required to be found out. So B will remain as B, and thickness is given as 8 millimeter, which has to, we have already converted to meter. So after this, what is the value? We have obtained the value as 24 into 10 to the 3 B. So B will remain as B, and what's the unit? Unit is Newton, tension in Newton. Okay, so Newton is the unit. Similarly, so this is with respect to T already we have obtained. Okay, next thing, in the problem actually it is said that you have to determine the width of the well taking centrifugal tension into account. Now, if if we have to consider centrifugal tension, then if you can recall the expression for centrifugal tension, we had this expression TC, centrifugal tension, equal to M V square. Okay, so M is nothing but, it is the mass of the bell per unit length. Okay, that is in kg per meter. Okay, so that is the thing that is required. Similarly, V also it is required, then only we will be able to find out this TC. Now this belt, like you can say, belt mass per unit length, M, it is not directly given, it also is required to be found out. But from where we'll be able to get this particular data? We'll be able to get this particular data from this belt material density that is given. Okay, so somehow we should be able to obtain in terms of kg meter from that particular. Similarly, V also it is required. So initially we'll find out the velocity of the belt V. Okay, so we know this can be written as pi dn by 60. So pi is a constant, d and n, both the things are already given. So we'll just put that particular value of the diameter of the pulley, and whatever is the envelope. Okay, so we have just put it, and we have obtained the velocity of the belt as 28.27. It's a linear velocity we are talking about, the peripheral one, so it is in meter per second. Okay, up to this much I believe it should be okay. Next, for finding out that centrifugal tension, we have seen that M also is required, V is also required. V just now we have found out. So that means we have to, we should be able to find out the mass of the bell per unit length, that is given by M. And how we can find out? We have been given the value of rho, that is the density of the bell material. So if we multiply it with the area, cross section area A, then we will get it with the mass of the bell per unit length. Because if you just try to see how we are going to get it mass of the bell per unit length. Actually, what is the unit of this rho? So it is nothing but kg per meter cube, right? And what's the unit of this area? So it's a meter square. Okay, so this will get cancelled, and actually what will remain? Kg per meter, that will remain, and that is nothing but kg per meter is nothing but it's just like mass of the bell per unit length, and that is what is required. So that's a dimensionally correct formula. Okay. So now we can write m equal to, that is the mass of the bell per unit length. Okay, not directly kg, it is kg per meter. Okay, so it can write like rho multiplied by a is once again b into t. So you can just put the known values, given values. So for rho it is already there, so b is unknown, b will keep as b, thickness is already given. So after multiplication we will get the value of m as 7.6 into 10 to the minus 3 b times the b is all, b will be there. Okay, b is required to be found out at time. And what is the unit? In this kg per meter. So as we now have both m as well as v value, so we can just directly using the formula for uh, centrifugal tension, we can just find out it. So centrifugal tension Tc can be written as, it's already we know, it's m into v square. So both the values we already have found out for m as well as v. So we'll be just using that particular value. And Tc, it's a tension, so uh, unit is Newton. Okay, tension is a type of force only. Okay, and we have obtained this value 6073.8 into 10 to the minus 3 b. So b will remain as b because b is unknown, no problem. Next, so up to this part it's done. Okay, now we know that the maximum tension, allowable tension is, if we consider the centrifugal tension, it is given as T equal to maximum tension allowable is tight side tension T1 plus the centrifugal tension. This is known. Okay. So from here, what we can have, we can find out actually this T1. Okay. T1 is nothing but the tension on the tight side. So T1, how we can write? T1 equal to T minus Tc. Okay. So T1 can be written as T minus Tc. So T just now, we already have this T1 T value. I think we have something here. Let me check. Okay, P1 and PC value will be just putting. Okay, so 24 into 3 times P. Okay, this one we just have found out. Okay, previously 24 into 10 to the 3 times B. Okay, that is the T value, and TC value. This is the TC value. That's now we have found out. Okay, so that is it. So we are just putting the value. B is common. So ultimately T1, that is the tension in the tight side, we have obtained as 23993.92 times P. Okay, in Newton. Next, what we will do, we have one very known relationship, important relationship for flat pipe. That is nothing but we already have the ratio of the tension. That relationship we already have. Okay, so tight side tension is given by T1, slack side tension is given by T2, and this ratio in case of flat bell, it is nothing but equal to e to the power mu theta. This is flat bell, so we know for flat bell, right? Resistance ratio of the two tension. Okay, tight side tension. This is for tight side, and this is for the slack side. Okay, it is given by T1 by T2 equal to e to the power mu theta. So this theta has to be considered in radian. So other values are already given. So T1 we already have. T1 directly we can use, and is a kind of constant you already have directly in your scientific calculator. Also you can directly put as e, or otherwise you can use the value of t also. And mu is given as 0.3, and theta has to be converted to radian. For how to convert to radian, 175 degree was given, so multiply it by pi by 180, so that will give you in radian. So T1 by T2 is obtained as 2.5. So from here we can write T2 equal to T1 by 2.5, and T1 just now we have found that as this particular value we have just obtained for T1. So T1 we are using, and T2 we have obtained. So in terms of B, also T2 also we have obtained in terms of P. So it is T2 equal to 9597.5 sin B. And what would be the unit? Unit is Newton. Okay. So up to this much, any doubt, anyone, any clarification needed? All of you have understood the things? I hope you have understood. Okay. So after that, very one small step is only remaining. So we have been given the value about your power transmission also, and we know power transmitted in case of wheel drive, it can be given as P equal to T1 minus T2 into P. So we already have the given, we have been given the value for the power transmission, and T1, T2 we just have obtained, okay, but it is in terms of P, and V velocity also we have. So these values are we are having, but only thing is an unknown will be there, unknown parameter B is there, and that is what is required to be found out. So other things are known. B will have the value in the P, and B can be found out. So what we have done here, so P, the power transmitted is given as 18 into 10 power 3, that is 18 kilowatt was given. T1 and T2 have just found out, so we have used this value, T1 minus T2, and B was there in both the cases, so B we have taken common. So velocity T we have obtained as 28.27 meter per second. So we have used this value, and after solving, we will get the bell diameter to dimension that we as 0.044 meter. Okay, and this completes this particular problem. Okay. So it's a easy only, but the thing is, you should know about the this different relationship. Okay, in well designing, always this particular relationship comes into picture. It will be very useful. So T equal to sigma Vt. Okay. Similarly, velocity you can obtain pi dm by 60, and centrifugal tension if it is required to be found out, then mass of the bell per unit length as well as velocity it will be required, and mv square by using mv square. So you can find out this particular value. Similarly, we know that the maximum tension is nothing but the addition of tension in the tight side plus the centrifugal tension, if you consider the centrifugal tension. So from here, our intention is actually we want to use this relationship of the T1 by T2, this particular ratio relationship, okay? Ratio of the tension in tight and slack side, which is the very, this particular relationship is very well known in case of your well trade. So it comes into picture, okay? So actually our intention is like that. That's why T1 and T2 also have found out, okay? And after that, power transmission for whatever is the relationship that we have, okay? So with this, the problem is over. Let me know whether you have understood or not. Have understood or not? Hello.
Yes, sir.
Okay, thank you. So, if you have any doubt, anyone, you can ask me, no problem. I hope no. Okay. Then we'll move ahead to very another problem. Okay, that's also easy one only. That is basically about finding out the length of the bell that will be required for a particular application. Okay. So, what is the question? So, question it states that find the length of the bell which is required to drive a pulley of 80 centimeter diameter, which is running parallel at a distance of 12 meter. Okay, that is the central distance is given. Okay, and necessary to drive a pulley of this means D2 is given. Okay, find the 12 meter from the driving pulley of diameter 480. So driving pulley diameter also is given, D1 also is given, that means, okay, so D1 equal to 480 centimeter. Similarly, D2 is 80 centimeter, okay, and central distance is given as 12 meter, okay. So from D2 and D1, we'll be able to get the radius of, okay, half of this will be the radius. Similarly, X value is, that is the central distance value is 12 meter, okay. So next, what we have done after that, it's very simple only. Okay, as nothing has been mentioned that whether it's open bell drive or cross bell drive, we'll solve for both, and we'll check with what is the length of the bell that will be required if the situation is a for a particular open bell drive or if it is for a cross bell drive. Okay, so we have all those relationship. Okay, the standard relationship we already know for finding out the length of the bell for open bell drive. That is nothing but length of the bell for open, L naught O for open, okay, it's nothing but pi whole into R1 plus R2 plus 2 times the central distance 2x plus R1 minus R2 whole square divided by X. So this is for open build rate. Okay, so considering the open build rate consideration, okay, we have obtained, we have used this particular value, and actually all the values are actually given. R1 plus R2 we have just used. Center distance is given. We can use, okay, and everything we have actually, if you look at here, okay, everything we have converted to centimeter, okay, or rather you can convert everything to meter, then your answer will be in terms of meter, okay, that will be better way to do, okay. So like that, or otherwise, as actually everything we have converted to centimeter, we already know about the this particular formula, okay, so we know that even if we convert to centimeter, no problem is there. So after that, if we use in terms of centimeter, okay, and putting this particular value and solving, we have obtained the length of the bell required for open belting is 3312.98 centimeter, which comes to around 33.13 meter. That will be required if it is open building. Next, we can also find out the relationship length required, length of the bell required for if it is cross bell. Okay, and for that we already know this particular length will be given as the expression is similar, but this R1 minus R2 becomes R1 plus R2 in case of cross belting. Okay, so changing this, actually we have solved it. The other things are similar, and by putting the values, we have obtained as 33.45 meter. So here we have seen that previously it is around 33.13 meter, and now for cross belting it is 33.45 meter. That means we have seen for the similar case, generally the length in case of cross belt, it is generally more than that of the length for open belting. So it's actually evident from the figure. Okay, so if we consider, suppose, sorry, suppose these are the driving pulley. Okay, so in that case, open belt is something like this, right? So it leaves from somewhere here. It is being wrapped around here. It will leave from somewhere here, and it is being wrapped around here. Okay, and cross belting is something like this. Cross belting will be, so for the same case, cross belting will be something like this. Sorry, don't mind my drawing. Okay, after that, this is being wrapped up here, and like this, it will leave here, and it will meet somewhere here. Okay, and like this. Okay, so for the same case, so the length for this of cross belting is somewhat more than that of the length for your open belt. Okay, understood? So we have some more problems related to design of the belting. Okay, finding out the dimensions and all. Okay, so those problems maybe in the next class we will solve the problem. Okay, so for today we'll stop here. Let me know whether you have understood or not. Okay.
Understood, sir.
Okay. So thank you everyone for joining, and we'll meet in the next class. So I'm ending the meeting now.
Thank you, sir.